Okay, so we left off yesterday talking about linear regression. Okay? So we'll continue that discussion today. I'll show you some more stuff with linear regression in Excel. Hopefully get us kind of familiarized with how we run a regression in Excel. I will be giving you one final Excel homework. It is much easier than any of the other Excel homeworks. It's a lot more of like interpreting some of the results that Excel will give you. So kind of pay attention as I'm walking through how we do some of this in Excel. I might even kind of create the or make the one Excel a separate video just so you can have help with that fifth and final assignment. But with kind of no further ado, let's just jump into things here. Right. So we started talking about yesterday. For every single observation, we can observe what this y value is, right? And we're going to try to come up with predictions, or y hat, based off of whatever coefficients we get for the intercept or the constant and that slope coefficient. Right? So we can predict what y should be, but we're never going to know what epsilon is for any one observation. So we kind of have this, oh, and I meant to have this on a slideshow, so let's go here. All right. So we said for any one observation, right, the actual y might be very different than the predicted, right? And the predicted y just comes from that line. If we know A and we know B, we could come draw that line. So for some observations, we'll have a positive error or epsilon. For others, whoops, we'll have a negative one, right? Will be kind of the actual y will be lower than the predicted y. But on average, we're making the best predictions that we can, right? For any one observation, it's going to be off, but on average, it's good. So the example I was giving with this is, the income education, right? I'm going to be way off if I try to predict Bill Gates's income with just his education. But on average, using education and coefficients I would obtain for the slope intercept, I could, on average, come up with pretty good predictions about what someone's income was given their education level. I'm going to be off for, every observation, but I can get kind of this line of best fit where I'm minimizing the amount of errors that I'm making with those predictions. So when I get the values for A and B, those are the values that would minimize these errors, or we said yesterday, the sum of the squared errors, right? So we kind of walked through all this yesterday. We said if we had two equations, two unknowns, we'd end up with this equation. Now, I can show you how we would do this in Excel, and so that's what we're going to kind of walk through here for a second. So let's say I try to kind of do this in Excel, right? So we'll pull open what we had yesterday, which was, I apparently forgot to open it. So we'll go linear regression, height and weight. There we go. There we are. All right, so we'll open this up. Go to the top. Okay. Pull it up a little bit here. So let's go to zoom, 150. Sorry about that. Thought I had that pulled up earlier. So the first thing we want to do is for every observation, go through, right, and take the difference between x and the average x, right? And it'll take that and multiply by the observation's value for y minus the average y. So we'll try to create that numerator first. So what we're going to do is we're going to create a column where we take x minus x bar and then y minus y bar, and then we'll take, I'm just going to do this in steps so we can see everything. We could probably do this a little more efficient, but so we can really see what's going on. We'll do that. So we're going to take the difference between, you know what I should do first? Let me do kind of average x and average y. So how do I do that? Well, if my y variable, we said yesterday, we were looking at that y variable being weight, so I'll select that. I'll then take the average of my x variable, which we were trying to predict weight by using height, so I'll take the average of that. Right? So here I'm going to say, take this observation's value for x, or height, and subtract the average height. Right? Now when I copy this down, for the next observation I want to do E3, but I still want to keep subtracting that same average. So we're going to put $signs in front of that cell reference. Hit enter. Whoops. Once I have that black cross, double click, do it for every observation. I'll do the same thing, but for my y variable of weight, subtract the average. Once again, I have to freeze this, so when I copy it down, it doesn't change. Copy that down, okay. And now, I just take that difference, multiply it by this difference. Right? Do that for every single observation. Right? So what was in my numerator was basically take every single observation, that column we created, and add them all up. Okay? And then the denominator, take the difference we found from x and the average, square it, and then add them all up. So let's see if I do, so we'll do sum of, I'll copy this so I don't have to type it all out again. Okay. So that's what we want to create there. So I'll go over a little bit so we can get there. Yeah. So here, I'm just going to take the sum of those differences multiplied by each other. That's my numerator. On the denominator, I want the sum of x minus x bar squared. Well, I don't have that column created yet, so will you upload this completed sheet? What we do? So on each side, got a question. So this isn't for Excel number 4. Excel number 4 was all the stuff that we did last week, which was looking at building confidence intervals and hypothesis testing for 2 populations. And then the last part of the Excel is what we did yesterday when we looked at matched pairs. The linear regression stuff will all be on a 5th Excel assignment, which I will get posted. And like I said, that one should be a little bit easier. And remember, I dropped the lowest of every homework type. So if you've already done the first 4 Excel assignments and you're happy with your grade, you don't have to do the 5th one, because if you get a 0 on it, it'll just get dropped. Or if you want to do the 5th one instead of the 4th one, you could do that as well, right? As long as you've done all the other ones prior, right? So the lowest of each homework type gets dropped. So your lowest Excel will get dropped, your lowest Connect, and then your lowest Learn Smart. Okay. But yeah, for help with Excel 4, those videos, Excel videos, are actually already up, kind of posted on YouTube from last week. Okay. And I will upload this completed sheet. I won't expect you to do anything like this. I'm just I want to prove something to you, kind of using the data. So don't worry too much about this Excel when I'm doing it. At the very end of today, focus more on that for the linear regression part of the Excel, or for the Excel part of linear regression. So I need to find kind of what this difference is between x and x bar and square it. So just to label it, I'm going to copy and paste that here. So go ahead, take this value and square it. Do that for every observation. And then add up all those values. Okay. So now I've got my numerator and I've got my denominator. Okay. So to get my kind of value for b, or my slope coefficient, I would take my numerator divided by my denominator. Should be about 4.71. Well, what did we do yesterday? Well, we used this data analysis tool, which, just to kind of show you again, File, Options, Add-ins, and if you're on Mac, you just started to go from Tools. I believe it's Tools at the top, and then you can see your add-ins. Manage these add-ins. Make sure we have the Analysis Tool Pack checked. Hit OK. So we can use this Data Analysis tab, which has this option of regression towards the bottom. Our Y variable, we said was, I have to go over it, looks like, weight. So I'll select that, and actually I'll select the label as well, because I said that you should do that, so I should probably practice what I preach. The X variable was height, so we'll select that. We selected the labels, hit OK, and sure enough, what coefficient do we get there? 4.71. So Excel really is just, when you use that data analysis tab, it's doing all this additional work to get that slope coefficient of 4.71. it just saves us a lot of time, right? And if we'll talk more about today, if we didn't just have one variable on the right-hand side, it would be even more complicated to do this, okay? Okay, so I kind of mentioned yesterday, I'd walk through that a little bit just to kind of prove, like, these are the equations that give you the answers. And we could do it this way too, but it's just kind of rearranging this mathematically, so it's not overly important for us to kind of go through. Right? So here we could do this, all this in Excel. Not a big deal. So this was for a different example. I decided to do the height weight one since we used it yesterday, and kind of prove it to you. Right? So what I just did was when we only had one variable on that right-hand side, or one x or one independent variable. Okay? But we can add a bunch more. Right? We can add as many variables as we want on that right-hand side. So why would we do this? So think about it. If I'm trying to predict income, well, yeah, years of education would help explain it, but so would somebody's age, so would maybe the region of the country they live in, whether or not they're in an urban area or not. So we know there's many factors that affect that y, or that dependent variable. And so when we start to add in additional independent variables, the interpretation of our coefficients stay the same. It's just now we add on this one little additional thing at the end, which is, here's the impact of a 1 unit increase in x, and beta 1 would be the impact that it has on y, holding everything else on that right-hand side constant. So we'll get a couple examples of this and see why this is so powerful. So instead of return to the crime equation, I don't think I actually brought that up yesterday, we used height and weight. So I'll kind of introduce this, right? Let's think about if we wanted to estimate kind of what the crime rate in an area would be, right? And we have a measure of police force expenditures, so this is the number of dollars spent on a police force. And then we have what the unemployment rate was in an area, okay? So both of these things we would think matter, and how would we interpret them? Well, first, so beta 1, right, would be if I spend, it's one more unit, so if I spend one more dollar on my police force, beta 1 is the change we would expect to see in crime, holding constant the unemployment rate. So why is that important? Well, if we didn't have the unemployment rate variable in here, it's likely that areas with higher unemployment probably have to spend more money on their police force because there's likely just more crime. It's kind of maybe a signal of lower social or lower economic conditions in that area. And so it might start to look like, well, when I'm spending more on my police force, actually that's have higher crime, but it's because we weren't controlling for what those economic conditions were. Excuse me. By actually including unemployment, now I can interpret this as this is the effect of a one more dollar spent on my police force, holding constant the unemployment rate. So the thought experiment is almost like I have two, and I think we would probably do this by like city or county. So I have two cities, one, right, or sorry, both of them have the same unemployment rate, but one of them spends one more dollar on their police force. How much higher or lower would I expect their crime rate to be? That's kind of the thought experiment we're doing. When we're adding in additional control variables, we're holding those factors constant. Okay? So, what does that look like? Well, we're still minimizing the sum of squared errors. So how do we choose what these b's or these betas are? Well, it's still the difference between the actual y and predicted y. It's still minimizing my errors squared, so the sum of the squared errors. But now, to get my predicted y, it's not just the intercept plus the first coefficient times the first variable, but I have all these other variables as well that help me make my prediction. So now I've got, instead of just two unknowns, right, I don't just have the intercept and one coefficient. I've got the intercept, the coefficient, the second coefficient, the third, the fourth, all the way to the nth. So I've got, I guess n plus 1 equations when I take the derivative of this in respect to each one of them, and n plus 1 unknowns, so I can solve that, but it's a lot of math, right? And it's not fun to do by hand, and that's why we have these kind of built-in packages or these programs that will do this regression analysis behind the scenes for us, and then spit back out at us what the estimates for these coefficients are. And before it's kind of hard, so before, remember, just kind of a reminder, what we were saying yesterday, and I think I started off today with this, so I'll erase some of this. Oh, actually, I got one here from yesterday. So we got all these this data, and we're trying to get this line that best fits it. Well, this was when we only had one x variable. Now we've got a ton. So the thought experiment is like, let's just say I had two. Well, now it's like I could graph my data points, but it would be in a three-dimensional space, and I'm trying to find the line that like best fits it through a three-dimensional space. But then it gets a lot harder to visualize when I have like more than two variables on the right-hand side. Let's say I have three or four. Well, I can't like visualize a 4 or 5-dimensional space. Or at least I have a hard time doing that. All right. So, but what we're still trying to do is like find that if we could envision this 5-dimensional space, we're trying to find this line that best fits the data by choosing all these coefficients values. So we're doing that. We're doing that through mathematics, right? And we'll actually have the visual way to take a derivative in respect to everything we want to choose, set them all equal to 0, and we have n+1 equations, n+1 unknowns. So you could look, I kind of referenced this for another class that's kind of a more advanced from UC Davis. Like he's got kind of a nice stuff of how you would do this when you have multiple variables, but we're not going to focus on so much how we solve for those coefficients because we have these programs that do it for us. The interpretation of those coefficients will always be whatever the x variable you're looking at is. It's a 1-unit change in that x variable would change the expected y value by whatever that coefficient, whatever that b or that beta value is. Okay? Holding everything else in the regression constant, so holding all the other x values or x variables constant. So as we add in more of these control variables, we get another statistic that really tells us something. It gives us some more useful information. So this r squared, and I don't know why I said of course, but it's our coefficient of determination, or it's how much of the variation that we see in that y variable can we explain with the dependent variables we've included, right? So if I get a r squared that's relatively high, right? R squared, it measures, it's the percentage, but it's kind of in decimal form, so it ranges from 0 to 1. 0 would mean whatever x variable or x variables you've included on that right-hand side, they explain 0 of the variation in that y variable. An r squared of 1 would mean you're explaining 100% of the variation, or you're explaining all of the variation in y, which that's ideal. If I can explain all the variation in y with the variables that I've included on the right-hand side, I can get really, really accurate predictions. But if there's a percent that I can't explain, well, now my predictions are going to be less useful, right? Because if I can only explain 50% of the variation, well, then there's still a lot that I'm not capturing. My estimate might be way off, right? And so we won't kind of focus too much on this, but we've got kind of this sum of squares from the regression and the total sum of squares here. Really, it's the difference between the predicted y and the average y. We add those, or sorry, we square them, add them up, and then divide by the difference between the actual y and the average y. And I don't want to focus on this too much because, like I said, we're not going to go kind of in depth, and we're not going to be calculating this r squared. It's always going to be given to us from Excel. But we do want to know that the r squared tells us what percent of the variation in our dependent or our left-hand side or our y variable that we're explaining with all the variables that we've included on the right-hand side. Okay? So the next thing we'll kind of start talking about, I use this example of the police force expenditures and unemployment. Right? So let's say I run this regression, I end up with an estimate for beta 1, or that slope coefficient on police force expenditures, that is positive. Right? Well, then the interpretation would be that if I spend an additional dollar on my police force, it increases crime rates. So how could that be true? Well, it could, because even though we are trying to hold constant unemployment, we're not capturing everything about that area, and areas that have higher crime to begin with, right, are going to have to spend more money on their police force, right? Now, if we could control for all these other factors that would help predict crime, and then look at the effect of an additional dollar spent, hopefully it would be negative, right? If I'm spending more money on my police force, I'm able to kind of reduce crime rates, okay? Or another example of this kind of omitted variable bias is, let's say I want to make those estimates on for a child's birth weight and whether or not the mother smoked. So that was an example we looked at yesterday. Well, let's say I find that this is negative. Does it really mean that smoking while being pregnant causes lower birth weights? Well, I think intuitively, probably yes, it does, but maybe it's an overstated effect, because what might also be true about mothers who smoke while pregnant? Well, if they're smoking while pregnant, they might not be doing other things that are good for the child either, so they may not be, eating is high quality foods. If we look at kind of smoking rates across income classes, if it's a little bit higher for lower income, then maybe we're getting people who don't have the availability to as high quality foods or as high quality healthcare. And so maybe all those things are causing lower birth weights, and it's not actually that the mother smokes. It's all those other things that are correlated with that mother smoking, right? So kind of another one you can, is this correlation or is it causation, right? I mean, we're getting this effect, but is it really the effect of the variable that we're looking at or these other things that are kind of just correlated with that, right? So when we interpret these coefficients, we want to be very careful about saying that they're causal, right? We're just finding evidence that these two things are correlated. We don't have the full power to say that they're causal, right? Now, the more controls that we add in, the closer to a causal, relationship we can make statements on, but it's still just evidence of a correlation. So here's a good example. If you look at like rates of autism and organic food sales across this time period, I mean, if we have this data in Excel and ran a regression, I guarantee you we get a pretty strong positive correlation there, right? But it's likely that there's a third factor, something that's related to autism rates and organic food sales that's driving both of these. Maybe it's an increased interest in just individual health in general, right? Or maybe it's not that autism rates are going up severely. Maybe it's that they are just being diagnosed better, right? People are getting to the doctor more. People are a little bit more aware and able to make the diagnosis a little bit better. But also people are caring more about their health might be driving the organic food sales as well. So it could be this third outside factor, right? So what goes wrong? Well, when we only have X and Y, it may not be that X is causing Y. It could be that Y is causing X, right? So if you think about my height weight example, it's likely that as I get taller, I get heavier. But I could have, if I ran the regression that instead that height was my left-hand side variable or my dependent variable and weight was my right hand or X, I would still find a positive correlation, but just weighing more doesn't necessarily drive your height up, right? But being taller would, drive that. So we might have the relationship flipped, but it also may be that X and Y are correlated, but it's because of this third thing, Z, that's not in the regression. So Z might be causing both X and Y, but if I don't include it in the regression, it's going to look like maybe X is causing Y, or vice versa. Right? So I always kind of like this little routine. So I used to think correlation implied causation. Then I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it wasn't that taking the class helped me understand this. It was something outside of that, this outside factor Z that was actually driving me to take the class, but also driving me to have this understanding. So, okay, don't explain the joke. It's not that good if you have to do that. So, don't worry too much about this. This is a complicated slide that was, I actually think I pulled this from a textbook. That's would be kind of the next level of stats. So if you kind of took the next business stats course, or I think they call it advanced statistics, ECON 321, I believe, you might start to look at some of this, and what we call is the omitted variable bias, right? And so this is the proof, and it doesn't matter. All I want to kind of get out of this is, here is our estimate for what the slope coefficient should be. Here's the actual relationship between X and Y. And the estimate that we get if we don't include this other variable x2, so here's our regression up here, we only included x1. If we don't include x2, when we get this estimate for the relationship between x1 and y, it's going to represent the true relationship, but also this additional component, right? And this additional component, whether or not that estimate is higher or lower, depends on the covariance, right? The relationship between the variable I included x1 and the variable I left out x2, right? Part of it is kind of driven by that. So I'm not going to ask you to kind of dissect this or use this equation, but all this equation is letting us know is that if we don't include this important variable x2 that's correlated with the variable we did include, then we're going to get and correlated with y, we're going to get an incorrect estimate or a bias estimate. So what we call this is the omitted variable bias, right? We've omitted a variable x2 and it's causing a bias in the estimate that we're going to get for the relationship between x1 and y. Or here, x2 is kind of, I was calling it a z. Doesn't matter what we call it, it's just notation. So I want to walk through an Excel example of the omitted variable bias. And I think it's a pretty interesting example, but it also allows us to get some practice in seeing how we run these regressions in Excel again. Okay. So the main question I have here is a college student's GPA impacted by whether or not they're an athlete? Okay. And then I say, okay, well, what if we include other controls, right? So we'll walk through this example. So on the Canvas and the in-class data file, I have this linear regression data GPA. Right? So if you want to follow along, or you're kind of watching this later and want to kind of look and see what this looks like or follow with it, you can open this up. Right? And I was going to do this as a separate, but I think I'll leave it self-contained. And I'll just mention every video that I have this week will have an Excel component within it as well. That's just related to the topic. Okay, so we've got this data set. It's got a bunch of different students, college students. Has their GPA, their SAT score, whether or not they're an athlete, what their rank was in high school, some verbal math test score, whether or not they were female, so 1 if they were, 0 if not, kind of racial indicators, 1 if they're white, 0 if not, black, 1 if they are, 1 if black, 0 if not, total credit hours they took, high school size, and I forget how this was measured. Obviously, it's not the number of students, it had some kind of ratio. Not really important, we won't really use this variable, it's just in the data set. And then the SAT score squared. So for the sake of what we're going to do, don't worry too much about these variables down here. I'm not going to use this SAT score squared, but it just was something that came in with the data. Okay? So my initial thought was, okay, I want to try to predict GPAs and how that GPA is impacted by whether or not a student's an athlete. Because you can imagine being an athlete in college might involve a lot of additional responsibilities and time commitments, and so maybe that has potentially a negative impact. But also it might teach time management and might force them to kind of be a little more attentive to their grades. So maybe there's a positive effect. I might want to know. I don't know exactly which way. I have kind of reasons to think it might go either way. So I go, okay, I'm going to do a regression. Right. So regression, hit OK. Select my Y variable. Well, I want to be able to predict GPAs. Right, so here's college GPA. I'll select that column. So Control-Shift, or on a Mac, Command-Shift-Down arrow. The variable I want to use to predict it, or my X variable, is whether or not they are a student athlete. So I'll select that. I selected my labels. I'll put it on a new worksheet. Hit OK. So here's my results. Right. So you kind of see I've got some things up here that we talked about earlier. So I've got a number of observations. I now have my R squared. And so it looks like just, whether or not someone's an athlete in college, I'm not able to explain a lot of the variation in GPA, right? What, 0.8% of the variation? So I'm not explaining a ton of the variation. But when I look at this, it looks like there's a negative effect. And is it statistically significant? Well, the p-value is pretty much 0, right? So if the p-value is pretty much 0, that's definitely going to be less than the alpha of 0.01 and 0.05 and 0.1. So I can actually reject the null at the 90, 95, and 99% confidence level. And remember, the null for all of these is, the null is always that coefficient is 0, right? So I'm assuming that's 0, but I'm rejecting that because I have a really low p-value. So I'm saying I'm rejecting that there's no relationship, or I found evidence that there's a pretty significantly strong relationship between this X variable and the Y variable. So it looks like if I'm trying to make predictions, what I could do is say, okay, look, if someone's a student athlete, they're a 1 unit change in the X variable, which would be athlete. So my regression would look like this, right? GPA is equal to, so the interpretation of that coefficient is if someone goes from not being an athlete to being an athlete, it's a 1 unit change in my X variable, then the change in my predicted GPA would be that it's 2.28 points lower, which is a pretty big decrease in GPA, really, if you think about it. It's on a 4.0 scale. Right? So I look at this and I'm like, man, we gotta really, being a student athlete, we gotta start advising people not to do it if they really want to keep a high GPA. But then someone says, well, look, I mean, it may be specifically if we got this data set from larger universities, um, you know, if my basketball and football program is generating high amounts of revenue, maybe my admission standards could be a little bit, more lax on those individuals, and so maybe I'm not getting as high quality of a student for my student athletes, specifically if we're kind of looking at these high revenue generating sports. May or may not be true, but what we can do is say, well, look, if I think that outside factor, that, well, look, I may be more or less likely to be a student athlete if my GPA is higher or lower. Sorry, if my SAT score, my kind of raw ability is higher or lower, raw ability in terms of intelligence. But that raw intelligence would also impact my GPA, right? So maybe what I want to do is hold constant, right? So hold constant the SAT score of an individual, which isn't a perfect measure of intellectual ability, but it's one of the measures we have here. So now if I include, right, SAT score to predict GPA, so let's say the equation now is A plus B1 times being an athlete. But I also have this second coefficient where I include a control for what their SAT score is. So now the interpretation of this coefficient B1 is that's the effect of being an athlete on GPA, holding constant the SAT score of the student. So now the thought experiment is like take two students with the same SAT score, but one of them is a student athlete, how much higher or lower was their GPA now, right? Holding constant the other factor. So what do? We go to our data analysis, regression, hit OK. So I'm using the same y variable of college, well, maybe I am. I think it's stuck. Why did it get stuck here? Oh, I think I didn't hit that. Why is this going crazy on me? All right, let's try this again. Data analysis, regression, hit OK. So my y variable, I want to select is college GPA, but now my x range is two x variables. So I can select these, right? Select the first two, and then hit Control Shift down arrow. So now I've selected two variables to put on that right-hand side, or my x variables. I select the labels, I hit OK. Now I get multiple coefficient estimates. So now it looks like, now the coefficient on student athlete is still negative, but right, much smaller. It was what, 0.28 before, it's 0.05 now. So now the interpretation is holding constant the SAT score of a student, being a student athlete only reduces their GPA by 0.05 points, but can I say that that effect is actually statistically different from zero? Well, with a p-value of 0.26, remember, I only reject if the p-value is less than alpha. So if my alpha is 0.01, well, can't reject that. Here we'll do this. Alpha, significance, confidence, rejection, decision. Right? So 0.1, 0.05, 0.01. So these would be 10, 5, and 1% significance levels, or 90, 95, and 99% confidence levels. So can I say with 90% confidence that this coefficient estimate is different from zero? Because remember, we always start out with the null that these coefficients are equal to zero. Well, if my alpha of 0.1, my p-value is 0.26, then I would fail to reject. So I actually could do this at each level, and if I fail to reject the 90%, I'm going to definitely fail to reject the 95, 90, 99. So here, I failed to reject the null, which is that there is no relationship. So just by adding this one control variable, I went from thinking, man, being a student athlete has a really large negative impact on GPA at every single statistically significant level, to it has a small effect, but I can't even say that it's statistically any different from zero, right? I can't even reject the null, which is that there's no relationship between being a student athlete and GPA. Right? Now, that's just one variable that I included, and notice also what happened to my r squared. Well, before it was 0.8% we could explain the variation in GPA that we could explain. Now I can explain like almost 17% of the variation, and so it's probably that this SAT score is probably a pretty good predictor of what your college GPA will be. It's not perfect, but it's a pretty good predictor. So just kind of mentioning some more, getting more familiarity with this linear regression. How would I interpret the coefficient on SAT score here? If we look at the original data, SAT score is measured in points. So this is the effect of, oh, I went to the wrong sheet. This is the effect of one, if I got 1 point higher on the SAT score, this is how much it would change my predicted GPA. So yeah, that effect's going to be small, right? Because it's the effect of 1 more point in the SAT score. But it could be that I score like 100 points higher. So what would the effect be if I scored 100 points higher? Well, if this is the effect of 1 point, and I want to know the effect of 100, if I've kept this as a linear relationship, I just multiply that by 100. So now if I score 100 points higher in the SAT score, it would predict my GPA would be about 0.19 points higher. And these, these are sizes that start to make a little more sense, right? Because, and we could play around with it with different values as well, okay? So, we could also start to do things like, well, I've got a bunch of other variables here, right? So maybe, and actually I'll rename these, so we'll do, athlete, no controls. So I'm not posting this on Canvas. Athlete with GPA, not GPA, SAT control. But I've got all these other variables, so I might as well, right? Go to my data now, let's go to my regression. I've got this Y variable hasn't changed, so I'm not even going to reselect that. But now maybe I want to include all of this stuff, right? So I'll just include, throw the kitchen sink at it, right? And actually, I don't want to include that squared variable because we're not going to talk about what that would do to the regression. So I'm going to redo this real quick. Sorry about that. I'm actually just going to include up to high school size. Okay. So now we've got coefficients for every single one of those variables. Now notice, what do you think probably happens to the R squared? Well, if we add in more controls, we're able to explain a higher percent of the variation in GPA. Okay? So about 30%. Okay? We can then start to do interpretation for all these. So I'll go through a couple of them just to kind of give you an idea. It's a little bit trickier. So for these 1, 0 variables, it's pretty easy. Like if we look at female, this would be, what's a 1 unit increase? Well, it's if it goes from 0 to 1, so 0 would be not being female, 1 would be female. So if a student was female, we would expect their GPA would be about 0.17 points higher. And notice the p-values here. Whenever you see this e to the negative, that means move the decimal point to the left. So e to the negative 20 means this is pretty much 0, right? So it's very statistically significant. I can reject the null that there's no relationship at every level. So there's a strong positive relationship from that. The other one that's kind of weird I want to go through, just because some of these start to get a little tricky. High school rank actually looks like it has a negative relationship, and once again, very small p-value, so statistically significant. So how would we interpret this? If I go up in my high school rankings by 1, I would expect my GPA would be 0.003 lower. So why if I go up in my rankings? Well, if we think about it, how are you ranked in high school? Well, 1's the best, 2's the next best. So going up 1 in the ranking is actually like moving towards the bottom. So that's why this is negative. That's a little bit tricky. Kind of one of those that's a little bit tricky. Right? And we could look at some of these these are kind of interesting, like high school size has a pretty small p-value, and it looks like it has like a positive effect. So we're going to go through and just kind of doing some more interpretation. We could interpret any one of these variables. It's just a 1 unit increase in that variable causes the predicted y value, or here the predicted GPA, to change by whatever the coefficient is, and holding everything else in the regression constant. Right? So the effect of 1 more point higher in the SAT score is it increases my predicted GPA by 0.001, holding all this constant. So it would be like, the thought experiment is we have 2 students. They're both student athletes. They have the same verbal math score, same rank in high school, both female, either both white or both black or both neither. Same high school size, same number of total credit hours, but one of them scored 1 point higher on the SAT. How much higher would we predict their GPA to be? Now that's the interpretation, the thought experiment of that coefficient. Now if we have all these p-values, even the e's are stored in here. So one thing I'll do on the fifth Excel assignment, but also is I think even on Max there's an option to actually have this output added in. But you could make your rejection decisions by if the p-value is less than alpha. So let's say I wanted to make the rejection decision at the 99% level. Can I reject the null for each one of these coefficients at the 99% level? So I could do rejection decision. I could use that if statement, or I could just compare. I could do this manually, right? I could look here and say, well, the p-value here is pretty much 0, so that's less than 0.01, right? At the 99% level. So I could, oh, what did I just do there? I think I hit my enter button twice. So that's a low p-value I could reject. The next one, well, pretty low p-value, so reject the next two, if I can spell. This next one though, a p-value of 0.1 actually would fail to reject, right? So maybe whatever this verbal kind of math test score, maybe it's not very useful in predicting GPA. Maybe I shouldn't be using it in making admission standard decisions, right? And so I could kind of keep doing this. But what I could have also done is similar to hypothesis testing. I could use this if statement and say if the p-value is less than my alpha of 0.01, put the word reject, comma, if it's not, right, the p-value is greater than my alpha of 0.01, put the words fail to reject. Hit enter, and now I've got my rejection decisions. And I could have even taken it a step further. Let's say instead of putting the 0.01 here, say reference this cell, and I put an alpha value here of like 0.01. Copy this down. Oh, why did this go wrong? Because when I made this cell reference, I need to freeze that, right? I need this one needs to always be the same. So, and also maybe if I put the spell correctly here too. Right? So now when I copy this down, it should be good. There you go. And now I can play around with, what if alpha was 0.1? At the 90% level, can I reject? Looks like none of them kind of changed there. I could even go back further. What about the 80% level? Oh, okay, then it changed one of them. I went from failing to reject to reject. So that's kind of neat. And I think if you use the built-in one, you can only choose one level of alpha. And I think it's probably defaulted to 95%. So if you want to do this at different levels, you got to make sure, even if it spits out at you these rejection decisions, make sure you know, oh yeah, what level is that at? Is that the 95% level? Because I might reject at the 95, but not the 99% level, right? So I need to make sure I'm kind of concerned with if it's spitting out that output at me. Kind of default, I guess I know that the Mac option I usually is to spit that out at you as well. Make sure that you know what level it's telling you the rejection decision at, because if I ask you for a different one, your alpha would change, and then some of these rejection decisions would change as well. And this one we'll call all variables. So also the other thing to really point out is also pay close attention to these e's to the negative. I mean, that is 0. Remember that if it looks like, oh, it's a p-value of 1.4, well, we can't have a p-value of 1.4, right? It's the probability that we saw something. Probabilities have to be between 0 and 1. So it wouldn't even make sense. It's 1.4, move the decimal 20 places to the left. Okay? So I always think this is kind of a good example of whether or not being a student athlete is a bad thing, because when we started out, it looks like it has a negative effect. But, well, there's this other thing we know probably matters, which is the kind of measure of what the incoming intelligence level of the student is, and that kind of eliminated the effect. If we then start to control for all these other factors, we then see being a student athlete actually has a positive effect. The p-value is pretty much 0, so it's statistically significant, like the 99% level, and it's a pretty sizable effect, right? Now we get the effect of being a student athlete. We predict that GPA would be about 0.18 higher, which is a pretty large increase in a 4-point scale, right? So these results are interesting. But once again, we have to remember these are not evidence of being a causal relationship. It's just that they're correlated, right? So this is just a correlation, right? It may be that student athletes, people who are able to play sports at college, maybe on average they tend to come from wealthier families because they were able to kind of um, have more resources to progress their athletic ability early on in life, and having a higher income kind of family also tends to lead to better outcomes academically, or you're in better schools and like we're not controlling for like the quality of this high school you went to. And so there could be still omitted variables. There could be all these variables that we're still not including that matter. So we need to make sure, yes, provides evidence of a correlation and is useful information, but we don't really know if it's completely causal. Okay. The third and final thing I wanted to do here was, let's say we wanted to make a prediction about what someone's GPA would be. And let's say I told you all this information about them, right? They have an incoming SAT score of 1200, they are not a student athlete, blah, blah, blah. So let's write this out, and then I'll kind of show you. So let's say, let's think of a person with a 1300 SAT score. They're not an athlete, a verbal math score, and I think that was on a scale of 0 to 1 if I remember right. So let's say, I don't know, verb math score of 0.5, and I can't type, I might actually type up here, it's probably easier. Of 0.5, what's the next thing? Ranked 20th in their high school, female, let's say they're black, so it's that. I don't know, let's say 12 total credit hours. I think this was, maybe as a semester. I think we'll go a little bit higher, we'll go 20 credit hours. And then high school size was also that kind of weird measure, so we'll do like 3.5. Let me get the raw data, see if I have these variables all right. So high school, yeah, so that's total credit hours. It's a total ones that are counting towards GPA. So we'll change that a little bit. So we'll go up here, 2.5, high school size, and we'll do, this is coming from 50 total credit hours. Okay? So we've got all this information about who this person is. What we could then do is predict their GPA. So how could we do that? Well, it's a little bit too big, so I'm going to go to here, change the view real quick. So let's make our predicted GPA for this person. Okay. Well, the first thing that would get added in is the intercept, right? Because remember, the interpretation of the intercept is if all these other x variables were equal to 0, the intercept is just the expected value of our y variable, if everything else that we include in the regression was equal to 0. So we'll take that intercept, and then we'll add to that, well, they had a 1300 SAT score, and here's the effect of 1 additional point in the SAT score, but this person scored 1300. So we multiply that effect of 1 unit by however many units that person had, 1300. We then add to that, well, they weren't an athlete, so what we really technically would do is say, take this effect of being an athlete, but multiply it by 0, right? Well, anything multiplied by 0 is 0, so I didn't really have to include that. Right? And then, okay, here's the effect of the verbal math score. I forget what I said they got in the verbal math score. Hopefully it was 0.5. I think that's what I said. Add to that their high school rank. I believe I said they were 20th. They were female, so we'll take that coefficient times 1, because that variable is 1 if they're female, 0 if not. So I believe I said this individual is black, and so white would be 0 times this, so we don't have to add that in, but we could, right? Take that coefficient, multiply it by 0. So they're black, so we'll take the coefficient on black, multiply by 1. Total credit hours, I think I said was 50, so we'll multiply the effect of 1 credit hour by 50. And then high school size, we'll take that coefficient, and I believe I said the high school size was measured at 3.5. So all you're doing is taking each coefficient and multiplying it by the value of that variable for this specific individual. You then add them all up, and don't forget you have to add in the intercept as well. and you'll get for this person, their predicted GPA would be about a 3.15. Right? Now, I have this all typed out. It would be even better if I had like just typed the numbers in, because then instead of typing numbers in here, I could have been referencing on a different cell, right? But that's how we would come up with our predictions for any one person or one company, depending, if we're looking at instead of individual data, like company level data. That's how we can come up with predictions. So it's pretty useful. I think that's all I kind of want to do here. I'm going to save this and end up getting this on Canvas, so I'll save this real quick for us. So you'll be able to look at it and see what we did here. Next week, we'll continue to do some more linear regression, just get some more examples of it. Really, this final exam is going to be a lot of hypothesis testing, so a lot of two-population hypothesis testing, as well as some of this linear regression stuff, right? Interpreting coefficients, determining using the p-value whether or not they're statistically significant, being able to calculate the test statistic, which we said yesterday, remember, is always just take the coefficient divided by the standard error. Making these predictions. And we'll get some more examples, like I said, next week of how we do this linear regression. Okay? So we're kind of leading up, getting closer and closer to the final exam. So another thing I wanted to mention is I'm going to get a figure out your grade tool up there. And so I want to show you kind of how this works. I think I don't have it in here yet. So let me go to show you the old one. Here we go. So this figure out your grade tool will look something like this. Right? So in Canvas, okay, you can see what your current Excel grade is, your current iClicker, so on and so forth. I will get these kind of updated. I know I still have to kind of grade that third Excel. I'm going to try to get that done over the next day or two. But once you have kind of your grades in each one of these categories, let's say my overall grade from the Excel category is an 80, my iClicker grade overall is 90, and I'll also get these iClickers kind of updated with some of the exceptions if you missed any classes. We're still doing in person, but also kind of factoring in these new weekly quizzes as well. So I've got maybe a 90 on the Connect, a 90 on iClicker, and I did all the Learn Smart, so I got 100 on that. Let's say I didn't do too hot in the first exam. I did a little better on the second. And here I don't know what my final exam is yet, right? So what this does, it kind of tells you your potential grade. So if you don't have the final exam in there, it's kind of assuming, right, that whatever your highest exam was, you would do the exact same on the final, which may not be true. And really, you don't have to like rely on that, because you can play around with, well, what if I did get the exact same grade on the finals I did on exam 2? Well, then I'd have a 76 in the class. Well, what if I did a little better, right? What if I got an 80 on the final? Well, that would bump me up to a 79. So what do I need to get a B? What if I got an 81 on the? What if I got an 82 on the final? Oh man, I'm getting really close. Hopefully Professor Linus likes to round up. What if I got an 83? Oh, even closer. What if I got an 84? Okay, that would push me up, right? So you play around with this, like potential scores on your final exam. Now, obviously, these Connect grades things, we don't have all of them factored in yet. We haven't completed all of them, but it at least gives you an idea of kind of around where you stand in the class right now in terms of a grade. And really, it's because I can only default it to be set one way for all students in terms of the percent that the exams count. So I'm just having it displayed the same for everyone, while some people might have done better on exam 2 than they did on exam 1. But this kind of factors all that in. It's very individual specific. It determines what your lowest, your middle, and your highest exam would be from different scores in the final, and kind of tells you what that potential predicted grade would be. Okay? So I'll get that posted up on Canvas as well. You can start to play around with that. And as you're working through kind of that fourth Excel, like I said earlier in this recording, that's from stuff we really did last week, but also stuff that we did Monday with matched pairs. We also have that fourth Connect homework, so if you have questions on that as you start to complete those, please don't wait till the last second. because I am going to get up one more Excel assignment and one more Connect. They'll probably be a little bit shorter. It's going to be mainly linear regression stuff. Now, like I said, if you're just kind of getting crunch time and we're getting closer to the exams, I dropped your lowest of each. So if you don't want to do the fourth, but you want to do the fifth, or vice versa, as long as you've done the first three of each assignment right, your lowest would get dropped. Okay. But if you have any questions, please feel free to email me, reach out. We'll have kind of one more week next week of recordings with new material. It's just going to be some more linear regression review stuff, and then kind of the following week we'll start in some exam review, right? And so I'll still be doing some of these tape recordings, but it'll be no new material after next Monday, Tuesday. Okay. All right, so we'll end the recording there for the week.